Welcome back everyone. In the previous lesson, we cover kernel PCA as well as an example of it using the iris dataset. In this lesson, we're going to cover another machine learning algorithm called linear discriminant analysis, or LDA for short. This is really a supervised dimensionality reduction algorithm and is commonly used in particular in the finance setting. It projects the input data to a linear subspace consisting of the directions which maximize the separation between classes. So it takes into account of the actual individual class itself using the training data and actually segregate it in terms of the dimensionality reduction. So it is most useful in a multi-class setting. Again, we're going to continue on with our same codes that we have, and also we're using iris so that there's nothing new here, at least there's not necessary for this part of the lesson. And we're going to import from scikit-learn discriminant analysis and import linear discriminant analysis. Okay, and we're going to instantiate this. Okay, and using the standard parameter, the classifier fit x as well as the y. Alright, so it's fairly straightforward so far. And what we're doing next, we'll just be plotting it in the 3D space that we looked at so many times. And this should be very familiar by now. So looking at this, it doesn't look like there's actually much difference here. So let me just toggle over here. This is the linear regression, you will recall. And if you look at this, notice that the actual dots itself is quite different from this. Okay, and in terms of the actual application, so let me just toggle back and forth. You know that the actual subspace was actually slightly moved, and also the actual segregation line is different. Notice now that the actual error rate is substantially lower than what it was before. Okay, so that's really a really quick demonstration of LDA. Again, the best way for you is to actually try it out. And what I've done here is that I've used an example from the scikit-learn library just to actually demonstrate the difference, just a quick comparison between LDA and also PCA. Okay, so what I've done here is that I've summarized the key difference between PCA as well as LDA. Now, PCA by design is an unsupervised method. It doesn't take into account of the target label, or Y for that matter. So how it works is that it identifies the combination of attributes. In other words, for that is principal components. That really accounts for the most variance in the data. So it basically look at what kind of combination of the underlying features that can actually explain the most variance. And you will recall that we talked about this. The first PACA usually has the largest, and quite often is the largest that can explain the largest amount of the variance. And then principal component 2 is usually the orthogonal to the first, but usually explain a little lesser in terms of the variance than the first component, and on it goes. Whereby LDA, we very quickly earlier demonstrated it, and what this tries to do is that it tries to identify the attributes. Attributes is another word for features or predictors that account for the most variance between classes. Notice the difference here. With LDA, it looks for attributes that account for the most variance between classes. So it's looking for attributes that actually can explain the variance between the two classes. Whereby PCA, which is the unsupervised method, look for attributes that accounts for the most variance in the data itself. Okay, so PCA is useful when you are looking at a homogeneous, or meaning just the data itself without any classes. LDA, you apply it with classes with the target in mind. So LDA is actually a supervised method using specifically known class labels. Okay, I hope that actually make it a little clearer, and hopefully you can understand that. So I've used these codes directly from scikit-learn. So I won't actually walk through the codes. It's not my codes. I just want to actually explain the actual variance between the two here. Looking at this, what you have is actually all of the data of iris, both the sepal length and width, and also the petal length and width all put in. And the actual PCA itself, of course, doesn't look at the type or the actual class itself. These are put after the fact. Later on, you can have a look at the code. And you look at the PCA itself, you'll notice that it actually segregates the three classes this way. It's a linear PCA, and specifically looking for two principal components. And these two principal components explain 92% and 5%. The first one explains 92%, the second one explains 5%. This is the LDA itself. Notice that they are slightly different. Let me just shrink this so that you can actually see them one on top of the other. Okay, right. You notice that the actual feature looks a little bit different, and that's really how LDA works. It actually looks for attributes that explain the variance between classes, which we actually have as a point here. Look for attributes that account for the most variance between the two classes. I hope that has been an illustration that helps you to understand the difference between the two machine learning algorithms. Quite often, they are very similar in the sense that what is used for is both for dimensionality reduction, but one is for unlabeled data, the other one is for supervised data. So quite often, you won't actually use them at the same time at all. Both are really powerful, both are really useful. I hope you now actually have two additional arsenals at your disposal when you are dealing with data that is, if it's unlabeled, you can use PCA. If it's labeled, then you can use LDA. Thank you once again for watching.